Susie, where are you going? This is the Susie. Watch. Susie. Okay. Now I think so. Live stream is on. So now let's do LeetCode session. This is the first session. Means I have started streaming now. Like I have to improve my uh, how I explain the code to others. Let me think how my approach is going on. So net is like low, but yeah, we can do it. Mm, mm, Easy. Okay, LeetCode. This is my profile. As you can see, I have been consistent from August, September, October, like in November, December, I was doing hackathon. I was purely focused on web development. Now in like January, February, you can see it. So today is like 27th of Feb. I solved 0 questions. Time is like 3 to 4:30 hour. One session, first session. Now let's move on. So diameter of binary tree, I have already solved it. So I will just make a revision and I will see how the approach should be and I will explain to you. I will explain to myself and I will think, yeah, if the approach is good or not. Like I'm giving the explanation to the interviewer, like you are the interviewer. Okay. Okay, that's fine. So now let's evaluate the question. Let's think, given the root of binary tree, return the length of the diameter of a tree. What is the diameter of a tree? The diameter of binary tree is the length of the longest path between any two nodes in a tree. This path may or may not pass through root. Okay. The length of a path between two nodes is represented by the number of edges between them. Okay, length of a path 1, 2, like 1, 2, 3. Answer will be 3. Okay, got it. So what should be our approach? Let's by saying it DFS, because DFS makes things easy. So I will go like from here 1, 3, 4. Okay, then like I will keep on counter 1, so counter will be 2. Then I will return. I will make it right returning now. I will make this plus. Okay. Okay, it will return a counter of 0. It will return a counter of 1 1. Okay, 1 1. Okay. So it is purely in DFS. So now let me think about how should I what should happen. So I'm gonna apply DFS, depth for search. Oh, I'm gonna apply. Okay. At first node, I will go with left. I will go with 2. I will go with 3. I will go with 4. Okay. Now 4, there is a null. So if next is of course null, then it will return 1 plus. Okay. 1 plus. So it will return 1 plus. Null है कोई दिक्कत है. It will like 2 का right. It will go from 2 to the right of 2 to root right, like to the 5. So now 5. So 5 will also give like null like 1 plus. Okay. So now while returning it, it will give max of both root left and right. Okay. So like here max of root left or right 1. Like 2 will give max of 1, max of root left max or root का right का max. 2 का right का max देगा या फिर root का left का max देगा. Okay. So basically it will give 1 and it will add its own edge. So it will be 2. Okay. But we have to store this. But overall, we are calculating, we will keep a max C that will count this root left plus root right plus this edge plus 1. Okay. So root left plus root right. So it will be 2. Max will be 2. Then 3. Okay. Then it will return 1. Okay. So it will be like 2, 1. So it will return answer will be 3. Okay. So overall approach is clear. Now let's like write and code. Okay. So what we will do? That's an interesting question. It's an easy level question. Yeah, it's easy. And I have not revised binary search tree, so I have no problems little bit, but it's okay. I can figure out the things. Condition. तो like null है तो zero return कर रहा है, okay, basically. Okay, I don't have a problem with it. Now it should escalate its value. Okay, left should be like +1. Are you getting it? Mm. Hmm. Of course, भाई code लिखनी पड़नी है. Some easy code to write, but still, like we are sorted with BFS and TFS. Okay. Okay. Diameter. भाई सोचो मैं कि लैग कर रहा हूँ, मैं आऊँ ना डायमीटर लैग कर रहा हूँ, मुझे मैक्स लैग कर रहा हूँ और मैक्स से को ये चाहिए. तो मैं क्या करूँगा इसको. मैक्स को तो कर ही सकता हूँ. Yeah, now it's like interesting. Maximum. Or we can do now. Max 3.3. Close to minus left. Diameter. Maximum. Left plus right. Return that one. ये important. Return कर 1 plus that's it plus part of it. नई फंक्शन मुझे क्या करना है. मुझे प्लस 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 करना है. first application image and come to max. YouTube. Word and DFS. Word of DFS. Okay, word of DFS. Then we have to return. Okay, to root. What is the root? Tree node. Tree node of root and integer max. That's fine. Okay. Now to give a base condition. So this condition will be like base condition. So base condition will be like base condition. If we do thing, return the number. Return C. The return teacher thing. Okay. In the end function. Now first check the first one enter return integer a diameter accident integer variable root 5 integer or maxilla max equals to max of so f plus देखो मैक्सी ये जो मैक्सी है ना ये तो इम्पोर्टेंट प्ले कर रहा है लेफ्ट प्लस राइट दे रहा है हर एक बारी का तो मैक्स ऑफ लेफ्ट प्लस राइट रिटर्न करते हैं देखिए रिटर्न वाला स्टेटमेंट मेरे को अच्छा लगा रिटर्न क्या करें वन प्लस मैक्स ऑफ लेफ्ट लेफ्ट क्या है सो मेरे को ये बेसिकली कोड लिखने में है राइट तो मेरे को कोड लिखने का सीखना पड़ेगा सो लाइक आई रिमेंबर द कोड राइट नाउ आई विल मेक पास दिस एंड we'll collect max. Okay. Let's remember the code. Let's submit and remember the code. If is not equals to root, if is not, basically क्या करना है पहले क्या करना चाहिए था मैंने तेरे को अप्रोच आ गया था दिमाग में राइट तो बोला कि लाइक लेफ्ट का राइट का तो तेरे को एक बेसिक पैटर्न आई हैव टू फॉलो अ बेसिक पैटर्न so that writing code should be easy because it's not should be like this that you have the approach but you don't know how to code it. Okay, so that was the problem right now. So you should remember the approach. Remember the approach, not it's like what you can say it template of a code. So let's remember the template of a code. So first we'll be like, what should I need? Let's analyze. Okay, we are going like DFS using. We'll go like at the most left. We'll store the left in integer. Okay, and returning statement should be like 1 plus. Okay, you are getting it will return 1 plus. It will return 0, but it will return 1 plus. Are you getting it? Yeah. Okay, no problem. So it should be like max of root ka left, root ka right. Okay. Now I need wrong. सो इंटीजर मैक्स डिफाइन कर रहे हैं 0 है तो रिटर्न करेंगे मैक्स है तो इंक्लूड है तो ऐसे जाएगा नाउ आई विल डू अ ट्राई रन वंस लाइक लेफ्ट विल बी लाइक 1 2 4 then 4 like it will go to right it will be like root of right, and it will be like base condition will be triggered. It will return 0, 0. So now both the condition is done for the fourth node with value 4. So now maxi will run. So maxi will be like left plus right. Left plus right is like 0, 0. So maxi will be 0. Okay, now it will return. Now it will return 1 plus max of left of and right. So your max of left and right is like 0, 0. So 0 plus 1. So it will return 1 to the node 2. So now 2 will go to the right because it already has gone to left. So it will go to right. Why? It will do the same thing and return 1. Of course, 1. Yeah, it will return 1. So you're saying like 1, 1. Okay. So 1, 1. So max will be like store 1, 1, 2. Okay. Okay. And it will return the max of this and this 2. This one is 3. So yeah. Basically, this is the code for using DFS. I think so. I think I should do BFS too. Okay. So Jan 11 में submit किया था हमने. Jan 11 क्या पढ़ा तुमने? Okay, BFS. Let's do BFS. Base condition if root return 0, 0. Okay. Parent and left. Parent and right. It's all left, it's all right. Okay. So root का left, root का right. Okay, now it's just something like complex situation here. So like, no, it's not worth it to like study PFS. So we can't waste no time. Time is important. So like, this question is done like for like 359 questions. Now what we are actually okay, in question. So I'm learning like graphs right now. So I'm learning graphs. So I should be like. I have to give time to DP because DP is one of the most important topic, and yeah, I should be like pretty interested in it. So this is the right now going on. So minimum stress to reach and from. I really don't like that question, so I'm skipping that question. Let's learn this algorithm, Bell-Manford algorithm, and see what happens.
Hey everyone, welcome back to the channel. I hope you guys are doing extremely well.
Let's carry on.
So in this video, we're going to learn about
make it clear,
the Bell-Manford algorithm.
what we are
Now, this is
studying.
again an algorithm which will help you to find the shortest path. Yes. I might be thinking, but Shriver, we already know an algorithm like Dijkstra, which helps us to find the shortest path. How is this different? It is the exact similar algorithm which will help you to find the shortest path from a source to all the other nodes. Yes, to all the other nodes. But the only difference is, if you remember the video of the Dijkstra algorithm fails when the graph has negative edges. Please remember,
negative cycle.
if the graph has negative edges, the Dijkstra algorithm will fail. And there was another point, if the graph has negative cycle, the Dijkstra forever. So Dijkstra detect, remember this, it helps you to detect negative cycles as well. That's a special directed graphs. Now you might be thinking, what if it's an undirected graph? Then how do you apply Bellman for edge weight will be 5, and I say 1 to 2, and the edge to 2, which will cost you 5, directed graph in or directed graph. Remember this. So if you're given the same edge weights, that is how you can always implement Bellman-Ford for any of the questions. Now imagine I draw your graph something like 2. So if I ask you the path weight, what will be the path weight? The path weight will be very simple. It will be -2, -1, +2. So -2 + 2 will go, and the path weight is basically -1. So if you apply Dijkstra, it will keep on rotating, keep on encircling in the path, because the path reduces at every stage. So thereby Dijkstra will specifically designed such that it will tell you that, hey, listen, this particular graph has a negative cycle. This is what you call as a negative cycle if a path has a negative cycle. Now let's try to implement the Bellman-Ford algorithm. So I will be taking this particular DG, which is the directed graph, in order to implement the Bellman-Ford algorithm. And we know that it is a single source shortest path algorithm. So the starting point is 0, and these are the edges given to you. So the edges will be given like U and V, which means there's an edge from 3 to 2 with an edge weight of 6. There's an edge from 5 to, this is nothing but this particular, when in any particular, all the edges are given to you as something in any order. Edges can be given in any particular order. Yes, edges can be in any order. Like it's not necessary that you have to follow any particular order. If you carefully see, you can have 3 to 6 at the top, you can have it here, you can have it here, you can have edges of the directed graph. The order can be anything. Very, very important. Edges can be in relax all. Very, very important. Relax
Yeah,
all the
this is the
edges
term I have
n
taken.
minus
Relax all the
1
wedges
times
and minus 10.
sequentially. Very, very important point.
Sequential.
Now, what do you mean by
Okay.
relax? Why n minus 1? Everything you will understand if you watch the video till the end. So what they're saying is relax all the edges n minus 1 times sequentially. Now, what is the definition of relax? Let me write that as well. So the definition of relax states if you have a distance array and if the distance taken to reach u plus the edge weight that you require. For an example, you're standing at 5 and you want to go to 3. The edge weight is 1. So this is the edge weight that I'm talking about. So if the distance of u plus wt is lesser than, very, very important, is lesser than the distance of v, which means as of now, you're at 5 and you're trying to go to 3 with a 1. So whatever distance you took to reach this u, which is 5, so basically distance of 5 plus this 1, if that is smaller than this, whatever you took to reach 3, then you got a better guy similar to Dijkstra. So what you'll do is you will simply go ahead and say, oh, you took basically that 5 is lesser than. So this way you have a distance array essentially. Now what is the definition of relax? Let me write that as well. So the definition of relax states if you have a distance array and if the distance taken to reach u plus the edge weight that you require. For an example, you're standing at 5 and you want to go to 3. The edge weight is 1. So this is the edge weight that I'm talking about. So if the distance of u plus wt is lesser than, very, very important, is lesser than the distance of v, which means as of now, you're at 5 and you're trying to go to 3 with a 1. So whatever distance you took to reach this u, which is 5, so basically distance of 5 plus this 1, if that is smaller than this, whatever you took to reach 3, then you got a better guy similar to Dijkstra. So what you'll do is you will simply go ahead and say, okay, I got a better guy. So I'll be like distance v is equal to the new distance, which is distance u plus w. This is what I call as relaxation of edges. This will be done for n minus 1 times. What do you mean by n minus 1 times? If you go over here and look at the n over here is 6 because there are 0, 1, 2, 3, 4, 5 like zero-based indexing nodes. So thereby n is 6. So you have to relax it for 5 times. 5 iteration of relaxations has to be done. Now, how to do it? Let's understand that. But before that, since you are calculating shortest path, what do you require? You require a distance array with everything initialized to infinity. So let's do that. So initially, when you initialize the distance array, the source will be marked as 0 and everything else will be marked as infinity because you haven't reached anywhere. So as of now, you know you're starting from here and that is always going to be taking a distance of 0, but you haven't reached something like 1, 2, 3, 4, 5. So what you do is you just initialize them with infinity. Now, how many iterations or how many relaxations you need to do? N minus 1. What is n? 6. So remember, you have to do 5 relaxation is what you need to do. Now, on the first relaxation, let me explain you. If I say first relaxation, what you need to do is, now on the first iteration, what you'll do is, you'll go across the first edge, second edge, third edge, and so on to the last edge. You have to go across all the edges. And that is when you say first iteration is done. On the second iteration, you have to go across again, third iteration again, fourth iteration again, fifth iteration again. You have to keep on going, keep on going, keep on going for 5 times. Okay, so when I say first iteration, what does that mean? That's very, very simple. You have to perform this thing on every edge one by one. That is what you call as one complete iteration. Okay, so the first iteration, what will happen? The relaxation of this edge will happen, then this. So let's do the relaxation of the first edge. Very simple. I know I'm starting like distance of 3. I will take 6 in order to reach the distance. Simple. I know I'm starting like distance of 3. I will take 6 in order to reach the distance of 2 because from 3 to 2 is where I need to go and I'll take a 6. So what is 3? If I look at 3, the value of 3 is nothing but infinity. So if I haven't reached 3, is there a point in going ahead with 3? I haven't reached 3. So there's no point, right? So the relaxation of this edge is done. Next, you go to this edge. It's like from 5 to 3. Cool. Let's again do the relaxation. From 5, you take 1 and you reach 3, right? So can I say 5 is still infinity? So you haven't reached. You can start from 0. You will take 5 and you will reach 1. So when you say distance of 0, it says, yes, I have reached myself. It's a 0 distance because I'm the source. Plus, I'll take another 5 and I'll reach the 1, which was previously reached with infinity means not reached. So I've got 5. So I can go and update this to 5. So on relaxation, I update one of the nodes to 5. Perfect. Next is this guy which has to be relaxed, which is distance of 1 minus 3 lesser than distance of 5. Very, very important. Distance of 1 minus 3 lesser than distance of 5. So if you carefully see, we have a 1 here, right? Do you see? We have a 1 here. So how much has 1 taken as of now? 1 has taken a 5. So it's like 5 minus 3 lesser than this. Update this with a distance of 2 and I can say the relaxation of this particular edge has been done. Next is this guy. So let's quickly relax this as well. This is nothing but you can write distance of 1 minus 2 lesser than distance of 2. Again, what is distance of 1? If you carefully see, it's nothing but 5. 5 minus 2 is 3, which is lesser than infinity. So you get 3. So go and update this to 3. Perfect. Done. Next, you will go across and do this particular iteration. So this is nothing but 3. So you can again write distance of 3 minus 2 again lesser than distance of 4. That's what you can easily write. And can I say, if you, why is this coming up again and again? Wait. So what I can say is, what is distance of 3? Can I say this? The distance of 3 is still now infinity, so this will not be done. Next is the last edge, which has to be relaxed. So let's quickly relax the last edge, which is nothing but distance of 2 plus 3 lesser than distance of 4. What is distance of 2? Let's see. Is 3. So 3 plus 3 is 6. What is 4? Infinity. So can I say this will be updated to 6? So what I can say is, the first iteration has been completed. And on the first iteration, we have got the updated distance values. Okay, now you have to again do it, which is the second iteration. And the second iteration, what you'll do, you'll again start, yes, you'll again start from the first. Now, what is distance of 3? Infinity, not reached. What is distance of 5? This time you'll find 5 has been reached with a distance of 2. Why did you find? Because in the first iteration, when you went, 5 was updated somewhere here. And now again, when you come back and restart, that 5 value which you updated here will be in use here. So what is the 5's value? 2 plus 1, which is 3, lesser than infinity. So this will go as 3. So go across and update 3 as 3. Perfect. Next one, this one. What's the value of 0? 0. So 0 plus 5 lesser than 1. That's still 5, not to be done. What is 1? 5. 5 minus 3 is still 2, which is lesser than, not lesser, so not to be done. Again, let's check out this. This time distance of 3 has been computed. What is distance of 3 this time? 3 minus 2, which is 1, says 4. Is it lesser than 4? Yes, because 4 is 6. So if you see 4 is 6, so what I'll do is, I'll say distance of 3 was 3 minus 2 is 1, which is better than the current distance. So I'll go and update this to 1. Very simple, because I started with 3 and I'll take a minus 2 distance in order to reach this guy. Again, the last guy is this, which is nothing but 3 plus 3, again 6, which is not better than this. So I can say the second iteration is also done. Similarly, you will do the third, fourth, and fifth. Basically, again ramp, again ramp, again ramp. And once you have done this, this particular distance array will be storing all your shortest distance. Yes, it will be storing all your shortest distance. And if you carefully look at this, it does not have a negative cycle. It does have negative edges, which is allowed, but it does not have a negative cycle. So ultimately, after all the 5 iterations or n minus 1 iterations, your distance array will be giving you the shortest path from this array. Now, a couple of questions. Why n minus 1 iterations? That's the first question. And the second question will be definitely how to detect negative cycles. What if the graph has negative cycles? How will I know about that? So, because the entire algorithm is pretty much similar to Dijkstra, because this portion is similar to Dijkstra. The only thing that we are doing is we are just doing n minus 1 iteration. So obviously, I want to know n minus 1 iteration, because the thought process is kind of clear. But why n minus 1 is my question. The thought process must be clear. Why? Because we just move ahead and this guy was updated. This updated 1. Then with the help of the 1, I got updated 5. Then went on moving iterations. So ultimately, but how did I know that on n minus 1 iterations, I will get my answer? That's my question. Because what if I would have done 2 iterations? What if I would have done 3 iterations? The question still lies, why exactly n minus 1 iteration has been done? So let's understand that as of now. So in order to understand the intuition, or why n minus 1, because that is the critical question here. Because we have understood the thought process. We knew 1 helped me to compute, because we knew 0 was the source which helped me to compute 1. 1 helped me to compute 5 and 2. And similarly, 2 helped me to compute 4, right? And when I came back, since I had computed 5, this 5 helped me to compute 3. And eventually this 3 helped me to compute 4. And so on, it will just go on this loop. Thought process is clear. But why n minus 1 is still the question. Let's understand this with this particular directed graph. So in this directed graph, if you remember, while explaining, I did tell you edges can be in any order. Edges can be in any particular order is what I always stated, right? So imagine I give you the edges in this particular order. So how many nodes are there? The number of nodes are 5. So how many iterations will we have? We will have 1, 2, 3, and 4 iterations, because edges are 5. So I have to do n minus 1, which is 4 iterations, correct? So now what I'll do is I will start off with the distance array. So let's quickly have the distance array. So again, to ease out understanding, I have kept 0 as the source and made it a distance of 0. Okay. Now let's do the iterations. So the first iteration states, this is the first edge. So it states, okay, distance of 3 plus 1, are you lesser than distance of 4? And it's like, distance of 3 is still infinity. No. Goes to the next, is still infinity. Lesser than distance of 2. I'm like, is lesser than distance of 1. I'm like, wait, 0 is 0. Plus 1 is lesser than infinity. End of the day, this one was updated. So first iteration, 1 plus 1 is 1. You to get, yes, you're good to relax the next edge. Perfect. Amazing. Now, to update it, to update 4 iterations. The distance array is ready. And this is your shortest path. Yes. This is your shortest path. Can I see this? I can. So thereby, did you understand why n minus? And then this will give you this. I find a lot of content over YouTube, but no one will say you why n minus 1. They'll be like, n minus 1, let's do it. We got the answer, coded, and that's it. This is very important. The thought process, how to detect negative cycle. Again, thought process. Since I knew negative cycle means if I keep on, because this will give you minus 1. Again, if I rotate, it will give you another minus 1. If I rotate another minus 1, on every rotation, what happen is, if there was 5 iterations, if you do the 6th iteration, the values will still reduce. On gets updated. Because after that, if I require on the nth iteration, if I do a relaxation, and even if I see distance gets reduced, sorry, distances, I should have gotten my answer. But if at the nth iteration, if there is still a reduction, it means we are running in the loop. We're running in the loop. That's why the distances are reducing, are reducing. So both the questions answered. So it's now time, and you can figure out the exact similar Java solution on the left. So given a weighted, directed, and a connected graph of V vertices and E edges, find the shortest distance of all the vertex from the source. So they'll be giving you a source. If the graph contains a negative cycle, then return an array consisting of only -1. And I think they've also stated if you cannot reach anyone, you have to assign it with 1 E8. So what I will do is I have all the edges. So I need the distance array. So let's quickly have the distance array of V, 1 E8 because I'm assuming I cannot reach them. So that's what I'll give. And now what I'll do is I will do the iteration or the relaxation for V minus 1 time because that is what I have clearly stated. That I'm going to do the relaxation for V minus 1 times on all the edges. Remember this. I'm going to do it on all the edges. So this is 0. This will be V and the WT will be IT of 2. Very, very simple. Okay. Now what's the next thing that I'll do? I'll have to do the relaxation of edges. So it's something like distance. Remember, you have to give the distance of source as 0. Otherwise, you'll have an issue. So remember, distance of 0 should be reachable, which means it should not be infinity. It should not be 1/8. And distance of U should be, you have to give the distance of source as 0. Otherwise, you'll have an issue. So remember, distance of 0 should be reachable, which means it should not be infinity. It should not be 1/8. And distance of U plus WT lesser than distance of V, if that's the case. If it's reachable, and if it's the case, I say, okay, cool. Distance of U plus WT is what I'll do. So this is how the Bellman for will make sure the distance has the answer. Ideally, you should have returned this. But in the question, they have stated what code would have finished here, but they have stated if it contains a negative cycle, then return an array consisting of only 1. So you have to do one more relaxation. This is the last, or you can say the nth relaxation to check negative cycle is what you have to do. Return an array consisting of only 1. Remember this. So basically, do one more relaxation, which is nothing but this. So you can say int u equal to it of 0. You can say int v equal to it case. You have to return an array which consists of only 1. That's it. And if that's not the case, because you cannot reduce at the nth iteration, you should have computed all the shortest path in n-1 iterations at the worst case. So what I'll do is I'll go and compile this and see if it is running fine. It is. Now let's quickly submit this. Looks like all the test cases do pass. So guys, that is it about the Bellman-Ford algorithm. What about the time complexity? V into E. Very simple. V cross E is the time complexity. The space is you're using an external V space and the edges is stored. So pretty simple. Now this is kind of a quadratic time, whereas the Dijkstra was E log V. So this is taking a bit more time than Dijkstra, but it is very useful if your graph does have negative edge weights, because Dijkstra does not work. So make sure if your graph has negative edge weights or if the graph has negative cycles, that's when you should implement the Bellman-Ford algorithm. Do you get follow-up problems on this? Usually not. In interviews, they will generally ask you to tell about the Bellman-Ford, or maybe they'll ask you about Dijkstra, and at the end of the day, they'll ask, what if the graph has negative edges or the cycles? What will you do? So it might be a follow-up question on Dijkstra. So very, very important. But I do not think the questions, like you will find questions straightly related to Bellman-Ford, because most of the questions are solved using Dijkstra's algorithm in shortest path. So guys, I hope you've understood everything. So
Okay. So let's solve now the same question that he has solved. Stravel Baba, will teach good. So Bellman-Ford. So एक बार question पढ़ता. So we will check out question first. Given a weighted and directed graph of V vertices and edges E, find the shortest distance of all the vertices from the source vertex. If a vertex can't be reached, then mark the distance into or 8. Note if the graph contains a negative cycle. Okay. And basically, we have a vector of n, which is the distance, and it should be marked like 0 to n. Basically, like here, 10 to the power 8 to 1, and it should be 10. This is the whole, we represent 10 to the power 8. Okay. Now let's move on to next. What should we do? Applying this Bellman-Ford's algorithm. Let for I equals to 0, I less than minus 1, and I plus this will be like this, and for I take two edges, I have to take out the edges. So the temperature U will be 0, 1, 9. 0 means I plus 0. Integral of V equals to I plus 1, and and check quality close to 30 of 2. So, paste and distance of V should not be equals to 1, 1, 2, 8, and then distance and distance of U. Wait. Okay, now we are done for the vector of distance and for like distance and for nth relaxation. We check out if it has if it has if it has डायरेक्ट लिख सकता था क्यों लिखूं okay source okay now we have solved this question then following to return what's this we will write time complexity also time complexity time complexity for this 12 Bellman for algorithm is mm, painful. That's it. Now let's learn Floyd Wash algorithm. It's not been that much time.
If you
लग रहा था बहुत टाइम हुआ है 15 minutes हो टाइम
everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be learning one more shortest path algorithm, which is the Floyd-Warshall shortest path algorithm. Now this is very, very different from the Dijkstra or the Bellman-Ford that you learn, because Dijkstra and Bellman-Ford were a single source shortest path algorithm where you were given a source and you have to find out till all the other nodes the shortest path. There was only a single source. But when you talk about Floyd-Warshall, it is different. Over here, there are 5 nodes So from every node, be it from 0, 1, 2, 3, 4, from every node, you have to tell me the shortest path to every other node over here. If I'm asking you from 4 to 1, you should be knowing. If I'm asking you from 1 to 3, you should be knowing. So there are multiple source. So this is why this is known as a multi-source shortest path algorithm. Remember this. It helps you detect negative cycles as well. Helps you detect negative cycles as well. So I hope pretty much you've understood what you need to find. Now, what is the shortest path? Very simple. If I'm asking you from 0 to 1, and I ask you what is the shortest path in order to reach from 0 to 1. So you can take multiple paths. One of the paths will take you 6. You can take this path, which is going to take you 5. You can take probably this path, which is again going to take you 5. Or you can take the shortest one, which is go here, go here, go here, which is going to take 2, 1, 1, which is an addition of, I think, 4. Yeah, that's the shortest path. So the shortest path from 0 to 1 is 0 to 2, 2 to 4, 4 to 1. This is the shortest path. If I'm asking you, that's the definition of shortest path. Any 0 to 2, 2 to 4, 4 to 1. This is the shortest path. If I'm asking you, that's the definition of shortest path. Any path that takes the least amount of edge weights is known as the shortest path. So what is the thought process behind the Floyd-Warshall algorithm? Now, it's very simple. It states go via every edge, go via every node rather, or go via every vertex or node, whatever you wish to write. So it's very simple. It states go via every vertex and node. Go and try and get the shortest one. So for an example, let's take, we want to find from 0 to 1, right? So if you're trying to find from 0 to 1, assume the distance you're trying to find is from 0 to 1, okay? So what are the possible ways that you can go? You can be like, Striver, I can go from 0 to 1 directly. I'll be like, yeah, that does make sense, right? Because that's a straight away path. 0 to 1, if there's an edge, I go via that. That's one of the ways. But if I ask you, go via every vertex, then you can be like, okay, I can probably go via 2. So which will mean I will go to 2 and then from 2 I'll go to 1. Does that make sense? Yes. And if I go from 0 to 2, it's going to cost me 2. And from 2 to 1, it's going to cost me 3, which will give me a total cost of 5, which is nothing but this particular path. That is if I go via 2. That is, and then I'll go from 3 to 1. Correct? So if I go from 0 to 3, that's going to cost me 4. From 3 to 1, that's
Let me search your mother. What is the link, huh? Seriously, photo here. This is the life of an plan.
going to cost me 1, which will be a total cost of 5. Again, can I go via 4? I can go via 4. So if I go via 4, let me write that in white. If I go via 4, it'll be 0 to 4 and 4 to 1, right? As of now, someone has computed that and given you from 0 to 4, it's a 3. Okay. So I'll be like, okay, 3 and from 4 to 1, it's taking me, I tried out every different vertex it is. So I can say all the vertex. And can I say this is nothing but I go from straight I to J? Assume. So can I write the path to be minimum of, if you try out all the K's, it'll be from I to K, very obvious, because you go from 0 to 2 and then from 2 to this, which is nothing but the J. Correct? So can I write this plus J of K? I can. That's what the path is. From I to K I'll go, and from J to K is what I have to go. And if I take minimum of all of them, 5, 5, 4, minimum of all of the go through vertex, then the answer, I'll have the answer. So somewhere down the line I've understood. But I need to implement this on a wider scale. What do I mean by a wider scale? Because over here, 0 to 4 was not a direct edge. Because 0 to 4 meant it went via 2. So it was going via 2. So somewhere down the line, in the past, someone would have also computed 0 to 4 and they would have implemented via 2. Via to understand. So 0 to 4 would have been computed and stored. So this is where you get an idea, okay, something like a dynamic programming, because we're using something which has already been computed. So you get an idea that, okay, this is a dynamic programming solution. It's not necessary that you know dynamic programming. I'm just saying, try to relate. We use, in this case, this one, because 0 to 4 was pre-computed. You did not compute at the point. Someone already knew what was the value to go from 0 to 4. That is what you need as a pre-computation. So you pretty much got the formula. Now what I'll do is, I'll try to give you a sense of the graph and then slowly and slowly, step by step, implement this algorithm so that you understand how is this algorithm implemented. Till now, in all the problems, we have been using the adjacency list in order to store the graph. But in the lecture 2, I've also taught you one more method, which is the adjacency matrix method. So you're going to use the adjacency matrix method in order to store this particular graph. Okay, it's very simple. In case you haven't seen the lecture 2, it's very, very simple. So something we know for sure is, if 0 is the node and I want to go to 0 itself, the cost will be 0. If I want to go from 1 to 1, the cost will be still 0. So from any given node to the node itself, the cost is going to be 0 no matter what you do, because you're already standing at the node. Something I know, 0, 0. So this portion will be storing the cost. So I can call this as a cost matrix. So 0 to 0 will be 0, 1 to 1 will be 0, 2 to 2 will be 0, 3 to 3 will be 0. So basically I'm saying this is 0, 0, 0. This is 1, 1, 0. This is 2, 2, 0. This is 3, 3, which is again 0. Pretty much understood, right? Now, what are the other? It says 0 to 1 is 2. So go to 0 to 1 and store 2. Go to 0, go to 1 and store 2. It says 1 to 0 is 1. So you go to 1, you go to 0 and you store 1. Okay. It says 3 to 0 is 3. So go to 3, go to 0 and store 3. Do not store the opposite vertex because it's a directed graph. It is a directed graph. If it's an undirected graph, for an example, split different values 0, 3, 2 to 2. You get graphs of 5. You how will graph
Infinity?
make sure everyone else is infinity, which means unreachable as of now, which means unreachable as of now. So this is the initial cost matrix, which you can always derive. Say UG, how will we implement the Floyd motion? Very simple. If there is an edge like this and it has a cost of 5, you say, okay, 5 this way, 5 this way. So this is how you convert a UG to a DG. Make dual direction edge. Okay. So if you have to apply Floyd motion in an
मैं कॉलेज जाता हूँ, एक लेक्चर करता हूँ, आ जाता हूँ यार। मैं तो कुछ है नहीं कॉलेज में मेरे लिए। तेरा कैसा था दिन?
ये सब हो गया कुछ नहीं चाहिए।
वैसे समझ में आता है भाई। मैं तो झाड़ू का पोछा लग गया। सुनी? गंदी रहती है तू। सोता हो यार, थोड़ा नींद आ रही है। 5 मिनट के लिए।
मेरा बैंक का टैक्स का है। अकाउंट की लॉग इन
हाँ?
अकाउंट को लॉग इन हाँ
वो कैसे?
क्या बेटा
तेरा कैसे है भाई?
कल कोई रिश्ता मैं आपको नींद आ रही है अच्छी तरह मुझे नींद सॉरी लेट हो बता दो तब सबसे देखती है ना साहब
मतलब वेटिंग। सभी नहीं।
जिस आगे उसकी
ये साथ में आप देख रहे हो? साथ में आप देख रहे हो?
गूगल करना
क्यों नहीं है?
साफ के आगे से ही
हो गई? कितना टाइम आएगा?
3:43.
Watch your thoughts. They become words. Watch your words. They become action.